Good afternoon from the Johnson Space Center here in Houston, Texas. I'm NASA's Josh Byerly. Coming up on December 21st, we will have two crew members of Expedition 38. Rick Mastracchio and Mike Hopkins are going to be going outside to conduct a series of spacewalks to swap out this ammonia pump that we've been talking about for the last few days. Here to talk about the decision process and also what's ahead for the crew members are Mike Suffredini, the International Space Station Program Manager, as well as Dina Quintella, the International Space Station Flight Director. And we are also joined by Allison Bollinger, the spacewalk officer who has helped choreograph what's ahead for the crew. We'll get started with Mike.
Good afternoon. I thought we'd spend a few moments kind of starting from the beginning when we first saw this anomaly, then we'll walk you through the steps to get you to where we are today. And then Dina and Allison can talk to you about the EVA itself and the preparations for the EVA. So the middle of last week, the pump on one of our external coolant loops was shut down. As you may recall, the ISS has two large coolant loops on both the starboard and the port side. We refer to them, of course, as A and B for lack of creativity in naming. And the pumps cool external ORUs as well as a heat exchanger that exchanges heat with a water loop inside and cools the internal components on space station. And we do that because ammonia is a highly toxic substance and we don't want it to be inside the vehicle, and so that's why we keep ammonia on the outside and the water on the inside. Of course, the one area where you have a risk that you could introduce ammonia into the water loop and therefore eventually into the environment inside space station is through the heat exchanger, and so we go to great pains to protect the case of accidentally freezing the heat exchanger. Freezing the water, of course, the water expands and you could fracture the heat exchanger and let the ammonia get into the water loop. And so we have a number of systems that protect us from that. So in the middle of last week, at some point as the coolant loop was trying to manage the temperature of the ammonia, it got to the point where the temperatures were remaining colder than it expected, and so the loop was shut down as expected, and the system reacted the way we wanted the system to react. And this was caused by a offset or a bias in what we refer to as the flow control valve. This is the valve that manages the flow of ammonia, either to send it through the radiators or as one extreme, completely through the radiators, or as another extreme we call bypassing the radiators, where the majority of the flow actually goes around the radiator and back through the pump, and this is how we control the temperature. It turns out that we had a failure of the flow control valve, probably the electronics in the flow control valve, which makes the valve think it's gotten to a completely closed state when it actually hasn't reached that, and preventing us from fully closing the valve then causes us not to be able to warm up the ammonia to the level we need, and depending on the environment we're in, the radiators where they're at, and other loads on there, you can get to the point where the ammonia itself gets too cold to enter the heat exchanger. And so we have spent the last week, today's Wednesday, so we've spent about the last week trying to figure out ways to either recover that valve or find other ways to manage the loads on the outside so we could keep the temperature below freezing coming into the heat exchanger, but also at the same time the heat load can't be too high or it doesn't do the cooling function it's supposed to provide. The ops and engineering teams have done just an amazing job of sorting through all kinds of options to try to recover the valve and look at other ways to manage the flow. Over the last several days, since we could not figure out a way to actually repair the valve or command the valve to overcome this bias, we started working on a valve, an isolation valve that's just upstream of the flow control valve, and looking to see if we could use it to manage the flow. We had tried to command it from the ground, and due to latency and other factors, we had a hard time managing the flow at the level and the repeatability that was necessary. And you've probably noticed a couple of nights ago the pump shut down. That was part of us trying to manage loads and really struggling with it. And so the last thing that we've done on board is we created a command patch that we sent out on board. And so when the ground commands this patch, It's done in such a way basically that we've taken the latency out of the out of the commanding sequence, and we've found that we do have a way to repeatably move this valve around. So now that we've done that, we're trying to figure out how to introduce the loads and see if we indeed can manage not only the nominal scenarios but the off-nominal scenarios, and the ground continues to do that. Meanwhile, as you know, we've been marching towards a launch of the first CRS mission, orbital CRS mission to ISS. That was scheduled to launch here on the 19th, and we had been trying to see if we could get to the point where we could reliably manage the flow of the ammonia so that we could rely on this loop in the event of the next worst failure. The next worst failure, of course, would be loss of loop B. And in doing the work and trying to figure that out, we carried both scenarios, both the scenario where we let orbital fly because we've managed the loop to the point that we've gotten ourselves to a point where we think we can control the loop well enough to handle the next failure, and allow the orbital to come up. We'd get on the other side of the beta cutout. We have a very high beta angle period that occurs always around this time of year. That we go into at about December 30th. And so we were trying to get ourselves to the position where either we let orbital come up, we're able to control the flow, we wait till we get to the other side and then replace the pump, or if we can't reliably figure out how to control the system, then we would go ahead and ask the orbital folks to stand down and go ahead and get the EVA done. So we sort of reached that point yesterday. Yesterday afternoon we realized that if we continue to press, we're starting to get to the point where we have to pick one path or the other. We have to get the crew ready. We have to get the ground team focused. And if we focused on flying orbital and found that we couldn't control the flow, even if we thought we were going to be successful, if we weren't, we'd lost the opportunity to do the EVA and change out the pump before the beta cut out. And so we chose that the better part of valor was to go ahead and pick a path. And so, as I said, we picked the path to ask the orbital guys to stand down, and we'll focus on getting the EVA done. So as Josh mentioned, the first EVA will be on the 21st, this Saturday. We think it'll take, let's just say it'll take about 3 EVAs. Could take a little less if we get lucky with the QDs, and could take a little more if we're not lucky with the QDs or we have any other kind of challenges that come up. And so we'll work our way through there, but the plan shows the EVAs today shows them every other day, and our plan is to go do the first EVA, and then we'll look to see when the next one needs to happen based on reacting to what may occur on orbit. Meanwhile, our orbital friends are rolling back, and they'll get ready for a launch after the beta cutout. We'll have to work that with the range out at Wallops, and Orbital's doing that now, and so we don't have a launch date yet for our orbital folks, but we believe we'll get the pump change out done before the beta cutout, and we'll be ready to accept the orbital guys just as soon as we can get the range set up and get them up to ISS. As you know, this pump has been changed out before. This is the starboard side. Back in August of 2010, we did a pump R&R for a different failure. That was actually a failure of the pump. This is a valve inside the pump module itself. And so this particular pump's about 3 years old. And so this is not an ISS aging vehicle issue. It's an unfortunate anomaly with the system with a relatively young pump. But it's, when you do mean time between failures, it's all about the averages, and so these are the kinds of things that can happen. So we're prepared to deal with it. We have 3 spare pumps on orbit, and so we'll take one of those pumps. Also, this particular failure mode is one we think we can overcome with an external valve, and so we'll save this pump and stow it and protect it throughout the EVA, such that in the future we perhaps could put an external valve upstream of the inlet to the pump and wire it and control it with that valve. So this is a very large ORU. I can't bring it in to fix it. I can't return it home to fix it. I don't want to throw it away if I can help it. And given this failure mode, we think we have a path through the woods that in the future when when we need this one, that perhaps we could put a valve on the outside and continue to use it. The pump itself was running very, very well, very smooth, was doing a good job, and we think has a lot of life left in it. So that's our plan forward. So I'll stop there and let Dina and Allison walk you through the EVAs themselves.
Okay, well, I'll start it off. So first of all, I want to give you kind of the general lay of the land in terms of our current status on board ISS. We're a little bit better off than we were in 2010 because, as Mr. Seferdini mentioned, the pump is actually running. So our external power boxes are getting cooling. It's the fact that we can't integrate with the internal water loop that is the problem because, of course, you know, we're running cold. That's the issue. And so we want to be able to close a valve and can't do so. And that valve allows cold ammonia to come in from the radiators. And so if you can't regulate that valve, then you end up in a scenario where you don't want to allow your water loop to come in contact. So anyway, so as you mentioned, we've been looking at other valves, and our on-console team right now in mission control has been working hand in hand with engineering folks to try to come up with different ways to try to command it. Our software folks have put a patch on board that allows for finer control of that upstream valve, the isolation valve that he was talking about. So, you know, in the meantime, our goal has been to try to get some of the heat rejected out onto that external water loop and see how much load it can take, and can we actually regulate it within the right temperature. So, you know, you're adding heat load to a loop, and it's a little bit experimental. So we're not there yet, but I'll just say, you know, our teams have been working very hard and are getting incrementally a little bit better each time, but unfortunately we're not at a fully recovered kind of state. So, one of the, you know, we talked about orbital. That could have been an impact to try to fly in that particular situation. But kind of one of the things we're focused on right now is what would happen if we had an additional failure. So, for example, if Loop Bravo were to go down, then we would have kind of this quasi-state of usefulness of the Loop Alpha, and then we'd also have Loop Bravo that went down. So we have a group of people called the Next Worst Failure Team, and they just try to get us in a good posture to make sure that we have everything configured just in case something went down, and make sure we have a procedure of what we're going to go run. And that team has really done a good job of figuring out what we're going to go do. So, for example, you can cool some of your internal avionics equipment using fans. We can hook up jumpers and that kind of thing. So we know what we would go do if we were to get into that scenario, but the goal at that point would be to go EVA and fix one of the two loops. So, you know, here we are, we're trucking basically towards the EVA, and I think, you know, this will be a good direction to go to get us into more of a nominal state of affairs. So just to kind of briefly talk about EVA in general, you know, the last EVA was EVA 23, and of course we did have the water entering into Luca's helmet in that EVA, and you can imagine that after that we kicked off a team to go take a look at how we can, you know, what is the root cause, what was the problem that we saw, and try to figure out what we would do if we saw it again. And so in terms of the root cause, that investigation is still ongoing. So, you know, we were able to, you know, one of the EMU suit guys, they really wanted to get hardware on the ground. Let's just try to see what we can do to get stuff on the ground. We tried to look at changing out items on board, you know, inside the EMU. We changed out a really critical valve and filter and determined that was not the problem. And we changed out a fan pump separator unit inside Luca's suit. We had a new one and installed that, and then we were not able to repeat the water and helmet situation on that particular suit. So we know that when we brought down the fan pump separator in November, that root cause investigation continued, and those folks took a detailed look at that particular unit. They determined that they did find contamination had plugged the tiny holes inside that unit, inside the water separator portion of that unit, and the clogging of those holes would cause water to back up and basically enter the fan and then get into the vent loop and would be able to enter the helmet. So that's not the root cause. We have to figure out what the contamination is. And unfortunately, it's a pretty complicated water chemistry problem, and there was not one particular constituent that you could take a look at and say, that's the problem right there on the suit. And so the team has still been trying to get more data on the ground. Specifically, we have a couple of filters. Well, we have several filters that have made it onto the ground. We periodically scrub the suits using an external line to try to keep them clean, and we were able to retrieve some of those filters and bring them down. And well, we've essentially taken a look at the filters that we already had and noticed that one of them was saturated with particulate. The interesting thing being it might be some sort of detergent kind of material, but the filter itself was full, and so the bad part of that is that it was kicking out some particles that might combine, especially in something like a water separator or something like a centrifuge, and create a lot of precipitate, which would cause our contamination issue. So we're still really, we have not at all come to conclusion on what kind of contamination or what the source might be, so I don't want to mislead you, but I'm telling you that we have done quite a bit of research on this, and we have decided to take a look at using Luca's suit again because it has the fresh fan pump separator in it, and that's what we spent overnight doing, is trying to get that suit ready to go back out. So Mike Hopkins will be wearing that particular suit, and we think that that's an extremely clean suit, and it's ready to go. So I believe that we've completed either most or all of our preparations on that. We did do kind of a return to service check after the fan pump stuff was changed out. We have high confidence that it's essentially just like a unit that was refurbished on the ground. So the crew did a really good job changing it out, and then we did a full return to service check on the suit, and are ready to go with those suits. So let's see, in terms of the EVAs that we're about to go do, as he mentioned, we've got 2 to 4 EVAs that we're anticipating. And for 2 EVAs, we would have to have a really, really good day in the first EVA, and Allison will probably talk about that. But of course, we could run into issues. But right now, I would just say we're nominally planning for 3, so that would be our plan. The procedures themselves and the readiness of the tasks, that isn't we're at a very high fidelity state where we're basically putting the final procedures on board. In some ways, we were lucky that we had the 2010 incident because that's really prepared us. We have already lessons learned. All of that's already been incorporated, and we had a team called the Failure I think it's Response Assessment Team, the FRAT team, and that team had already put all those lessons learned into all of our documentation, and we've had a chance to get together with that team and figure out what else is still open. So a lot of that has been analysis that our engineering counterparts have been performing, but from the ops side of the house, those procedures were really well potted. So we were already postured very well. The crew was able to start looking at those the day after we said that we might go EVA. So I feel like we're at a very mature state in terms of being ready to go EVA. I looked around the room today and said, what are people worried about? And really, there was not much to be said. So I think we're ready to go out the door on Saturday, and our team has no lingering, outstanding, show-stopping issues to be working right now. So with that, I'm going to hand it over to Allison.
All right, thanks, Dina. Okay, so to briefly mention a little bit about the water mitigation steps that Dina talked about, we have made some modifications to the suit. So in addition to training that we have given to the crew on how to respond in the event that they have water in the helmet again, we have upgraded 2 pieces of hardware that we are going to be installing in the suits. So this right here is a helmet absorption pad, and this is basically, it's a modified absorbent pad that is designed to be installed on the back of the crew member's helmet. And so this is our first line of defense, that if water were to enter the helmet again, even though we don't expect it, if water were to enter the helmet again, this is designed to hold anywhere between 600 and 800 milliliters of water. We have included nominal checks in our procedure where we normally have the crew inspect their gloves to make sure they don't have any damage in the gloves. We've now also added steps for them to check the helmet absorption pad, or the HAP, to verify it's not squishy. That's the technical term that we're using to define whether we think water has entered the helmet. So typically we've done some testing, quite a bit of testing on the ground with astronauts to verify when you lean back, when can you first sense squishiness? And that's roughly around the 200 milliliter mark. So if we have anywhere close to 200 milliliters of water in the suit, that's definitely much more than we ever expect to be in the suit. So as soon as the crew member senses squishiness in his HAP, that's a sign that there is a problem in the EMU and it's time to come inside. So they do have that response, and we created a new emergency cuff checklist page for the water in the EMU. So as soon as they either see water in their helmet or sense water in the HAP, it's time to start terminating the EVA. The other piece of mitigation hardware that we put into the suit is the snorkel. So this is a modified piece of hardware. It's a waterline vent tube, which is a component inside the EMU that we had the crew fabricate these on orbit. So they basically cut apart the plastic tubing on this waterline vent tube and then attach hook Velcro on one side and pile Velcro on the other. And the idea is that this snorkel is now installed inside the suit with the crew member between his water restraint bag and the front side of his suit. So this is your last resort, that if water is encroaching your face, as similar to happened with Luke on the last EVA, that the crew member can lean down and use this to breathe, to receive fresh oxygen down near his midsection. So those are the two pieces of hardware. We had the crew fabricate 2 of these snorkels a couple days ago, and these helmet absorption pads, we were fortunate enough to launch quite a few. We have 24 on board. We were able to launch those on the last Soyuz as well as on the orbital demo mission. So we're in good shape as far as that goes. So with that, we can go ahead and start talking about the details of the spacewalks. So if we can show the first graphic. So there are our spacewalking crew members. We have Rick Mastracchio. He comes to us with 6 spacewalks under his belt, so he's a very experienced spacewalker. He will serve the EV1 or lead spacewalk officer or lead spacewalker role for EVAs 1 and 2. And on the right side, you see Mike Hopkins. He is a rookie spacewalker, but very excited to go out the door. He will be the EV2 for EVAs 1 and 2, and then he'll take the lead EV1 role on EVA 3. So then on the inside, if we go to the next graphic, on the inside we'll have Koichi Wakata, who is flying the SSRMS, or the Space Station Robotic Arm. He will be, as you'll see in the video, one of the crew members spends a large majority of all 3 of the EVAs on the arm. So Koichi will be tied into this, and he'll be flying the arm. So the next graphic shows the overviews of the 3 spacewalks. So broad strokes, what we plan on doing on the first spacewalk is focused on deintegrating the failed pump module. So that includes demating the fluid quick disconnects, installing a pump module jumper box, which allows us to have fluid flow between the rest of the TCS, the thermal control system, with the accumulators in the system, and then demating the electrical connectors on that failed pump module. And then we will also spend a little bit of time working on the spare pump module, which includes releasing some multi-layer insulation. On the second EVA, we're focused on removing the failed pump module from the truss and then temporarily stowing it on the POA, or the Payload ORU Accommodation temp stow location. And then we work at the end of the EVA on releasing the spare pump module from the ESP3 carrier on the outboard side of S3. And then we fly that over to the S1 location and install that into the truss, and we plan on hooking up only the bolts and the electrical connectors on this EVA. And then on the third and final EVA, we will complete that spare pump module installation, which includes mating the 4 fluid lines, and then relocating the failed pump module from its temp stow location out to the ESP3 location where the failed came from. So with that, we can go ahead and get started with the videos, and we'll talk through the tasks. So if we could start the videos. All right, so on the first spacewalk, the crew members egress the joint airlock, and they make their way up to the center of the S1 truss. Mike will be the free float crew member. Rick will ingress the arm. Koichi will fly him up to the work site. And then the 2 crew members will spend some time demating those 4 fluid quick disconnects, which are illuminated there. So a quick overview of the interfaces on the pump module. You have 4 fluid quick disconnects. 3 of them are 1.5 inch size. 1 is a quarter size. You have 5 electrical connectors. And then you also have 4 fasteners, which are 5/8 inch fasteners, which are what the primary fasteners that hold the pump module into the truss. So here we were fortunate enough on the partial gravity simulator to have Doug Wheelock and Tracy Caldwell-Dyson help us create a training video about lessons they learned during the last pump module R&R. So we were able to film this training video just a few days ago, and we got that uplinked to the crew so they were able to learn of any gotchas. Once those 4 fluid lines are disconnected, they'll then work to install the 1/2 inch and the 1.5 inch fluid lines to this pump module jumper box. And as I mentioned, this is what allows ammonia to flow, now that the pump module is out, allows ammonia to have access to the accumulators in the nitrogen and ammonia tanks to prevent liquid lock. So that's what we spend most of EVA 1 doing. On EVA 2, the focus is getting the failed pump module out of the truss and the new one in the truss. So there you can see the Loop A pump module on the S1 truss on the right side. And as Mike mentioned, we have 3 spares. We're shooting for the ESP3 spare pump module to install in its new home. Right outside the airlock, Mike will pick up the adjustable grapple bar from the ESP2 carrier. He will then translate up to the truss, and Rick will be on the arm, and they'll work to release the 4 fasteners that are holding the pump module on the truss. Then they'll slowly slide the pump module out of the truss about halfway, giving them access to the install location for the adjustable grapple bar. And it's this grapple bar that allows the pump module to be temporarily stowed between EVAs. So once the pump module is free of the truss, they'll give Koichi the go to relocate the arm and Rick over to the POA, or the temporary stow location, for this pump module. And Mike said this is our desire is to keep this pump module as a viable spare so that we could perform additional maintenance on it in the future. So once they have the spare pump module stowed on the POA, they'll then work to translate over to ESP3 where the new pump module is located. They'll release that from the carrier and then fly back over to the truss to install that new pump module in the same location where we removed the failed. As you can see, there's quite a bit of arm maneuvers throughout all of these EVAs, so I'm sure Koichi will be getting a workout. So they'll work together to slowly guide the pump module into the truss, and then they'll attach the 4 fasteners that hold it in place and then mate the electrical connectors, which will give us good insight into seeing if we have a viable spare in this pump module. No, we won't have camera views like this.
How much TV, so I know where the pictures are.
Right, we'll have helmet video and as well as cameras on the arm. So the third spacewalk is focused on getting the fluid lines hooked up to the pump module, those 4 fluid lines hooked up to the pump module, and then working on relocating the failed pump module from its temporary stowage location over to the ESP3 location where we retrieved the spare. On EVA 3, we'll be swapping roles, so Mike will actually be the crew member in the arm this time, and Rick will be the free float crew member. As Koichi is flying Mike over with the failed pump module, Rick will spend some time at the S1 pump module install location, verifying that he has everything buttoned up and that we've cleared the MT translation corridor. Once they're at the ESP3 work site, Mike will slowly give commands to Koichi to bring him into the work site. Then the 2 crew members will work together to release the adjustable grapple bar, and then they will work on rotating the pump module 180 degrees to allow them to install it into the rails on the ESP3 work site. Once they install it, they'll attach the 4 fasteners that hold it in place, mate some electrical connectors to provide heater power to this failed unit, and then install some multi-layer insulation over it to protect it. Mike will then work to retrieve the adjustable grapple bar from a temp stow location. And Koichi will then begin maneuvering him from the outboard location on S3 all the way back to the ESP2 carrier on the airlock. During this time, Rick will be cleaning up the work site, which includes packing up the tool bags that they brought out with them and then heading back towards the airlock. Once at the ESP2 location, Mike will install the adjustable grapple bar onto the FHRC, or the flex hose rotary coupler, which is its temp stow location. Once complete with that, he will work on egressing the arm and removing the foot restraint, and then the 2 crew members will head inside, and that will complete the EVA. And Josh, I think that's all I have.
Okay, let's take some questions. We'll start here in Houston, then we'll go to the phone lines. Let's start with Mark Crow.
Thanks. This is probably a minor question in the whole picture, but could you just talk about the beta angle and how that's influencing the timing of what you're trying to do, if there is influence?
Yeah, there is. Both EVAs and berthing operations have constraints that make it difficult to do. In fact, we avoid berthing altogether above 60 degrees beta. The constraint's really 65, the ground rule is 60, but we're headed to a pretty high beta. and you can get yourself into conditions where you didn't make it the first day, and then suddenly you're deep into high beta territory. So we try to avoid berthings around the high beta period, dockings or berthings around high beta periods. We looked at doing an EVA during high beta. There's a lot of challenges associated with that, both for cooling the ISS and meeting the needs for the EMU crew itself. And while we could probably work it out and make it happen, given the short time we have, we'd prefer to stay on this side of the beta cutout.
I'm sorry, Mark Carreau for Aviation Week. Could you just frame that period as you see it?
We go above 60 on December 30th, and I believe we come below on the 9th of January. It's about like that.
Okay. Jim?
Jim Oberg with NBC. Dina, looking at the root cause work still going on, are you looking at any kind of root cause, such as the airlock heat exchanger, that would be an issue of contaminating the other suits as well as this one? In other words, if the other suits are contaminated the same way as Lucas was, could you tell by inspecting on orbit? And what are you doing to lower that possibility?
Well, so the airlock heat exchanger, of course, is one of the components that we'd be looking at. And what we're basically, I'll just say, as I mentioned, the water chemistry's been very complicated. And in fact, whole days have been spent with a lot of water chemists trying to figure this out. So we have not yet said it's something that for sure would be fleet-wide, and in fact, it could be something that's a one-off. But we've looked at everything from constituents that are inside the suits to the airlock, and we have found different types of components that might lead us well. It could be an airlock heat exchanger thing, or maybe it wouldn't. But in terms of what our scrubbing and taking a look at all the different filters and everything that we've done, we think that we're taking out 2 clean suits to the best of our knowledge. Not that we wouldn't, we can't rule out until we've just determined the root cause we can't rule out that we would have water and helmet again, but that's what the ops mitigations are for and what the new hardware is for. But we're still really working on what the root cause is. So I just say that that's kind of where we are at this point.
Are the issues of potential water flow in the helmet constraining you, for example, for a crewman on the end of the SSRMS? Have you changed your SSRMS crewman procedures because of any concerns about getting back?
Yeah, I'll answer that particular one, I think. So we have had so originally when this all broke post-EVA 23, we did look generically at what it would take to get somebody who's on the arm, if he had water and helmet, even if he's carrying a large pump module, for example, and the other crew member can come and assist and help to tie down the pump module. Or if, for example, let's say that the unaffected crew member is on the arm, then the other person, on the truss, if he needs assistance, then we would tie all that down. But we did a very specific analysis for this particular EVA, and we also looked very carefully at the arm trajectories to make sure that we had good trajectories that would allow us to get back to the airlock as soon as possible, should we need to. And we even did a neutral buoyancy laboratory. We did some neutral buoyancy laboratory work to make sure that we could be as efficient as possible in terms of our tie down, should we have this eventuality. But that's all just part of saying, hey, we've looked at this from a safety perspective, and we have all the mitigations in place for that.
Okay, Gina?
2 questions. Mike, what have you learned about this? You've got a phrase about this, just another day of learning how to operate a space station. What have you learned from this event?
Okay, so you're talking about the suit or the pump?
The pump.
This is part of how things happen in space and what can possibly fail in which way. And so what we have learned, we've been operating for 15 years on ISS, right? And when we first started Space Station, the philosophy was you had a failure, you changed out an ORU, and you sent it home and you forgot about it, right? And you let the team operate the way you need to on orbit. Logistics is not a consistent system that's always there for you, and crew time is very constrained. And so over the years, we've changed our mindset. When you have a failure, you try to understand the failure, and instead of the first thing you do is try to just change it out because it takes crew time and it's waste to spare, you say, can I figure out how to work around it? So we've learned a lot with this particular system. We never imagined that we could figure out how how to control a loop without a flow control valve. If you look at the data, the thing is moving all the time. The isolation valve was made to be opened and closed very seldom. And so the design wasn't such that you'd sit here and move it in little increments to try to find the sweet spot. And so in this particular case, I tell you, I think we've learned a lot about how to manage the system. We hadn't ever intended to manage this way. If I'd had a lot more days before the orbital guys flew, I'm starting to get the sense that we probably could have figured out how to operate this thing for an extended period of time this way. I can't say that for certain, but I'm kind of getting that sense. So this is one of just many failures. We have a lot of different types of little failures, and we learn what our options are. And we wouldn't have imagined this as being an option when we've talked about flow control valve failures. We've just assumed that eventually you got to change it out. It's just like a pump failure. But then it happens and you go, wow, changing a pump out tomorrow is going to be really hard. In this case, we had the suit anomaly we still haven't completely sorted out in our head, so we would just assume not rush off to change it out if we could help it. And so it kind of gave us the impetus to look even further. So it's just another opportunity for us to figure out how to operate this vehicle and not the way it was originally intended, but certainly in a safe manner, and perhaps preserve spares in the future in crew time. So.
Allison, I look at the parts you've got there. Were those parts you had on the space station, or what were the constraints for you and your team trying to figure out how to come up with those workarounds and those solutions?
Right. So the snorkel, as I mentioned, this is actually a part that we can change out on the spacesuit. It's part of a waterline vent tube assembly, which is actually what runs from the backpack of the suit, and it's what hooks up to the liquid cooling and ventilation garment that the crew members wear. So normally these tubes will be passing water that's providing cooling around the crew member's body. So some smart engineers on the ground were able to figure out, hey, it's a similar diameter to a snorkel that you have for scuba diving. So what if we're able to, each waterline vent tube assembly has 2 of these tubes. So by just sacrificing one of our spares on board, they were able to come up with a way to just snip off the ends and then file it so that it's not rough in the crew member's mouth, and then apply Velcro. We already have Velcro inside the suit, which is what holds the drink bag up to the front part of the suit. So they were able to come up with this ingenious idea to hold it in place. As far as the helmet absorption pad goes, we looked at ways of modifying, potentially on board, modifying the maximum absorbency garment that the crew members wear, but that created quite a bit of FOD. It was kind of a mess to cut this apart. So we were fortunate enough to be able to quickly turn these around and fabricate units that we were able to launch, as I mentioned, on the orbital demo mission as well as on the Soyuz mission. So thankfully, we already had these on board. But both of these, the invention of these came out of the issues that we had on EVA 23.
All right, Robert.
Hi, Robert Perlman with CollectSpace.com. For Dina or Allison, with regards to the number of EVAs, where do you see the potential holdups, or where do you see the potential ability to get ahead so that you might have you might just need 2 EVAs?
All right. So the way, let me ruffle through my papers here. So the way the timelines are laid out to currently show us in 3 EVAs is based on the difficulties that we had with the fluid quick disconnects during the previous time that we changed out this pump. So we have become a lot smarter on how to operate these QDs, especially in off-nominal situations. So in the event, fingers crossed, these QDs go very smoothly and we're able with no issue to close and demate these QDs, and we have enough consumables at the end of our EVA, it allows us to pull the removal of the failed pump module and the temp stow on the POA up to the first EVA. So then that puts us in great posture to, on the second EVA, be able to just go fly over, grab the spare from ESP3, install it in the truss, hook up the fluid lines, integrate that into the system, and then button up the work site within 2 EVAs. That then does leave the failed pump module on the POA, on the temporary stow location until a future EVA. But keep in mind that we did have, during the previous EVAs in 2010, we did leave the failed pump module on the POA for, I think it was about 6 months before we relocated it. So we still have plenty of time to keep that as a viable spare if it were to remain on the POA instead of being relocated to the carrier on ESP3. So those are the potential ways to get us into 2 EVAs.
And from Mike, you mentioned that this pump's going to be potentially repaired, but if that wasn't the case, or you couldn't do that, do you still have the ability to launch a new pump module? Do you have pump modules on the ground waiting?
Yeah, the one that failed, actually, we're repairing, and we're going to have to do another build of pumps just for the life of ISS in general. Over time, you eventually have to build a new set of pumps. But yeah, the cargo capabilities we have today can carry every ORU we have in the fleet we can take to orbit. There are a couple of spares we had not intended to build or didn't think we would need. One was the solar array, and the other is the big radiators. If we had to spare either of those two, we'd have to figure out another path than the existing systems we use today. But other than that, all the ORUs we have and expect to change out on orbit, we can carry to orbit.
Okay, let's go to the phone lines. Let's start with Elizabeth Howell with Universe Today.
Hello, can you provide some more specifics on which systems have been affected by
Did you catch that?
Which systems have been affected by this pump issue?
Yeah.
Well, I'll just say, one of our, the main issue is that we can't really integrate the Node 2 heat exchanger, and it affects the systems in Node 2, Columbus, and the GEM right now. And that's where we do a lot of our science, is in those modules. So it's really affecting our ability to do science. And then additionally, our other systems are dependent solely on Loop Bravo, so that opens us up to kind of a window of failures that would not be good. Basically, we're in a loss of redundancy situation for the others. In terms of the external systems, like I said, we're in a better posture than in 2010 because we have a lot of boxes externally that are continuing to be cooled. So we're not in as bad a situation in terms of our critical systems being down right now. So really, I'd say mostly our impacts are to the payloads and the fact that we might have had an issue flying orbital, which we would have had to jumper around and that kind of thing. For the most part, we're operating nominally from a crew perspective minus the payloads, which is, of course, our primary mission. So that it is a big impact from that perspective.
Okay, let's go to Miriam Kramer, space.com.
Hi, thanks for taking my question. Yeah, I have kind of a similar question to Elizabeth. I'm actually wondering if any potential science has been lost because of this, or if there's still time to bounce back from it. So have any experiments been lost, and will there be time to potentially make up for it? Thanks.
To date, no, we haven't lost any research. We've had to manage what research we do based on what Dina was saying. We have had some periods of having the freezer, we call it the Melfi, that keeps our existing samples cold. We've had to have it off for extended periods of time, which it's built to do. It's built to go about 8 hours without any power and still keep the components at the temperature they need to be kept at. Of course, on the flip side, then when you turn it back on, you've got to run it for about twice as much time to regain that capability to get it back up to temperature. So the team's been managing that because that's one of the components we've had to power on and off based on where we were and trying to manage the flow a little bit. Largely, though, the Melfi's been on in the last little while, and the teams have done a good job of protecting that research. But we have not lost any research as a result of this.
All right, Peter with Christian Science Monitor. Peter, you there? Okay, let's go to Jeff Linfield with National Public Radio.
Hi there. So I was wondering, if you lost the other cooling loop, would you be forced to abandon the station? And also, if there was a leak, how quickly could you get the astronauts back inside, a leak in the helmet? Thank you.
First of all, go ahead.
So what we have been trying to protect for is next worst failure. Next worst failure is the loss of that pump. I would tell you that given how we can manage the pump today, that we would be in pretty good shape if we lost pump B today. If you're already down a complete cooling system and you lose the other cooling system, then we run into quite a few challenges. We'd have to rely largely on the Russian segment, and we'd be in a pretty big hurry to try to get outside and repair it. And so that would challenge us if we had both loops down. We've always known that was a big concern, and so we try not to leave ourselves in that posture very long. It's part of the reasons why we've been kind of balancing the risk of trying to fly orbital if we can limp along on the A side with this way we're trying to manage it. And success, or at least the criteria using to say we could limp along was, could you stand the B side failure with the way we can manage the A side today? And so that was the question we were trying to answer. Yesterday afternoon, we weren't certain that was necessarily the case. Today, I'd tell you I'm still not certain that's necessarily the case, but I feel better about our chances if we have a problem. And again, remember, pump A is not completely down. Pump A, in fact, the pump itself is running fine, and we're cooling all the external ORUs. The last time we had a pump failure, and Dina talked about this, you lost all the cooling to your external ORUs. There's a major power systems and power distribution systems outside that lost cooling, and so that has a dramatic impact. And those components remain active, and so therefore we are supplying power to many of the systems that we had to manage last time. So this is not a complete loss of the A side to begin with. Because of the way we're learning to manage it, we have more confidence today than we did yesterday, and I suspect tomorrow and the next day we'll gain more. So I would tell you today, if we lost the B side, we would manage it almost like you're listening to us manage the A side today. We would, if you lost the whole pump, again, you lose half the cooling to half your power systems, and so that would have a more dramatic impact than you see here today, but it's something we can manage. In general, it doesn't do us a whole lot of good to evacuate space station. If we lose the two coolant systems, it does us a lot more good to stay there and fix them so we can get on with things.
Okay, Marcia with Space Policy Online.
Thank you for taking my question. I'm curious as to whether or not
уже не то что вторичным СМИ, может каким-то просто захудалым газетенком там всяким.
I'm not sure what this interference is. I'm hearing someone else's voice. Anyway, I'm wondering if you should characterize this spacewalk as an emergency, and that's why you came up with the absorbent pad and the snorkel, or were you working on those things already? And is it going to be part of your spacewalking plans from now forward to always have those in the spacesuits?
Can I answer that one?
Sure.
You guys want to? The way I would answer that is we had this failure where we flooded the suit. Before that EVA, we believed that we actually wouldn't have that failure mode. What we believed would happen was as we started to pass that much water past the little impeller and the fan, little fan and the fan pump set, we believed that it would stall the fan, the suit would shut down, and that then began your 30-minute timer that you had with the secondary oxygen pack to flow oxygen, and we would come back in. So the timing was always try to protect 30 minutes, get inside, and we believed that you wouldn't necessarily flood the suit. We believed you would flood the system, and eventually it would shut down before you passed a lot of water. What we learned was we can pass quite a bit of water for an extended period of time, and the suit would keep running. And so we have reviewed not just the hazards associated with this anomaly, but all the hazards for the suit with an eye towards this and anything we've learned over the years, because the suits are 35 years old. We've reviewed the hazards every so often as a matter of course, but when you get a new data point, then you look at it with a different lens, and we've done that with all of our hazards. So I would tell you, based on what we've learned, I would expect that for as long as we have this particular design suit, we'll keep the HAP and this snorkel available to the crew as an alternate means of providing us additional margin against the failure case where you have to come back inside. We've also done a number of tests. In particular, one of our concerns going in with the failure case we dealt with was whether or not we always had this vent where you can open up and let vent and let the air flow through this little vent on the side of the helmet to keep the flow across the crew's head so you don't get stagnant air in the helmet, and eventually you have these kind of failures. And we were worried about opening it and flowing water, if there's water in the helmet, flowing the water out. Well, the good news is you get the water out. The bad news is if you freeze it and you can't close it again, you could be in a worse posture. So we've done a lot of testing and proved to ourselves we can't freeze it open and it'll pass water. So we've done a number of other tests, and all of this is data that we've put back into our hazards and re-looked at our hazards and made sure that we have all the controls we need to protect the crews. And we still are at the point we think we can protect a 30-minute case where you have to be in within 30 minutes. and even with these new scenarios. But part of what gives us a little margin in the system is this HAP and the snorkel, which are relatively simple to do, and so I would suspect for the future, as we use EMUs, I would imagine we'll continue to put these components in there to give us margin, even as we mod the suit and feel better about that particular anomaly.
Okay, thanks, Marcia. Just a friendly reminder to everybody on the phone lines, keep your phones on mute until I call on you. That sort of helps everybody out. Let's go to Stephen Clark with Spaceflight Now.
Hi, thanks. Just a question on the delay of the orbital flight. Can you talk a little bit about the impact of that to some of the payloads inside the Cygnus? Will you have to replace any experiment samples inside there, and also any expected downstream impacts to the visiting vehicle manifest for 2014?
I wouldn't expect a big impact to the downstream manifest. The orbital guys might have a little slip in their next flight, but it wouldn't be significant. Unless something else happens, it wouldn't be significant. We do have some late load items. We have some freezer blocks that we use to keep things cold so they don't stay frozen forever. So we'll take those out and refreeze them, and then store the items that are in those containers until we're ready to go fly, and then we'll pack them back up and send them on their way. Also, interestingly enough, we have ants on board, and while most of us try to kill ants, we're trying to keep these alive, and so we will. It's an ant habitat. It lasts for about 10 days, so we'll roll back, and as I understand it, we feed the ants, and we'll take care of them until we're ready to pack them up, and then the 10-day clock will start again. We'll late load, and I think it's a 12-day clock actually. So we'll go back into our normal flow. So we didn't lose any research. We did have, we had confirmed with Orbital at that point that we could go all the way to the end of the window and protect all the research, but now that we're not launching, we'll back up. We can get back to the items, and then we'll keep them conditioned until we're ready to fly.
Okay, Irene with Reuters.
Thanks very much. I have 3 quick questions. The first is the AMS operating now?
You want me to elaborate?
I'm sorry, we can't hear you. Whoever is speaking Russian is not on mute, and we can't hear your responses.
Yes, AMS is still operating. At some point we had, as we get to the high beta, we have to maneuver the one of the radiators, one of the central system radiators, to give them a little bit of protection from the sun. That was going to be a concern when we were trying to manage this loop. But assuming that we get the EVA done, then we'll be able to protect them like we normally do. But they're operating today, unless there's been a failure in the last hour or two I hadn't heard about.
No, I think they're operating.
The other question, I think, Dina, did you say that Mike was going to be wearing Luca's suit? And for Allison, when were those snorkels that are going to be used, when were those fabricated, please? Thanks.
Okay, so yes, Mike Hopkins will be wearing Luca's old suit, but it will have a brand new fresh fan pump separator. Additionally, there are some other components that we changed out on it, mostly just from a sizing perspective, and because we were low on oxygen on the secondary oxygen pack. So we did do some other change outs, but notably would be the fan pump separator and all the water lines contained within that unit. So you know, like I said, we've done a thorough return to service examination of everything that happened on EVA 23, and then considering that we changed something out on orbit, we feel confident that the suit is a very clean suit and ready to go. And then the other one was the snorkel?
Right, and the crew fabricated the snorkels on board on Sunday prior to their on-orbit fit verification on Monday.
I'm sorry, I missed that. They were fabricated on Sunday?
Sunday.
Thanks.
Do you have another question?
I do actually. This wasn't part of it, but if there is a problem with the suits, is there another backup plan? Is it possible for the astronauts to use the Sokol, the Russian suits, or what would be the options if there's continuing issues with the leaks and the helmets?
Well, I would be. I'll say I would be surprised if we have a problem with suits once we change out the fan pump set. what we are learning is this problem is caused by flowing water that has a high silica content through a centrifuge device, which is the fan pump set turns out to be, and then you create particulate. We think it occurs over a number of exposures. We've looked at our filters, and the only saturated filter we found we brought home in August of 2012. We had exposed both 3011 and 3005 to this this overly saturated filter. There's actually two filters in the system. We brought home the downstream particulate filter, and in there we had discovered, based on what was in there, that the ion filter in front of it was saturated. Unfortunately, we didn't know that at the time, and so we continued to use the ion filter. Both 3005 and 3011 were exposed to this. We believe it is highly likely this is where the contamination came from. How it got introduced is something we're still trying to sort out. But we believe with clean filters, the ion filter will trap the silicate. As was mentioned by, I think Dina mentioned it, we had found that there's an excess, in this one case, there's an excessive amount of chlorides and sulfates, which is not really important, other than if you know that what happens in an ion filter when those show up is they have an affinity towards the ion filter, and so they kick the silicates off. And when the silicates get kicked off, they get kicked off in large quantities, go into the flow stream, and then once they get to a centrifuge type device, they nucleate inside the pump, and then you start plugging up holes. So first of all, we believe that the lines we're using today are clean. We've put in new filters, and we think the filter system works. 3015, had the failure. It's possible it might have played a role in this at some point. 3011 now has been completely, all of the components inside have been completely changed out. And most importantly, it's been the fan pump set. So 3010 really wasn't exposed to this particular line after we know it was saturated. Now, it was exposed once to this line before we knew it was saturated, but it was early on, and so we feel pretty good about 3010. So I said all that to say, as we go outside and we flood a suit, if it's 3011, we'll all be shocked. But if we do flood a suit, then what we'll do is we'll go back inside and we'll look at the data. If it's 3010, then what we'll do is, and we still plan to do this, we just got to get them on orbit, and one of them is on Orb 1, and it's the reason why we were trying to fly Orb 1 first, is to fly a clean fan pump set. So we've got what we believe to be a clean one in 3011. We've got one that we know is clean, that's on Orb 1, and we'll fly, as we sort our way through this anomaly, we intend to fly at least one more, if not two more, fan pump steps to make sure we know the condition of the fan pump steps in the suit. And when you do that, then at least for this particular failure mode, even if we don't know root cause quite yet, we think we have a number of EVAs in these suits. And I would tell you that given what the team is learning on how to manage this pump, I think we will probably be able to buy ourselves time. If we have a problem in EVA, we'll probably back out, and then we'll talk about what plan B is. If we can get a second fan pump step on Orb 1, we might try to do that and get it late loaded and then fly Orb 1 and then go back outside and do the EVAs. But if we can prevent having to do that, having to manage this loop in this degraded state, we'd prefer to do that.
Thanks so much for my short questions.
All right, thanks, Irene. Let's go to Ivan over in Russia.
Hello. This is Ivan from TASS News Agency of Russia. I wanted to ask you how the recent malfunction affected the Russian segment of the station by far, and if the forthcoming EVA will not be successful, how exactly will that affect Russian segment and Russian cosmonauts?
Let's see, on the Russian segment, we do provide power to the Russian segment. But again, this failure mode on this pump, where we're reducing cooling is inside the space station, not outside. The exterior components, the MBSUs, which provide power distribution and also are a source of power over to the Russian segment, are working. And so today, we are managing the power, and we're trying to minimize all of our loads throughout the station, but we continue to provide the power that the Russian segment needs to operate. So from that respect, we haven't really impacted our Russian segment colleagues at all. I will say that there's a Russian segment EVA planned for the 27th of December. Our Russian colleagues were kind enough to move it to the right so we could fly the orbital mission, and of course then this anomaly occurred. It is our plan to try to get all this work done before the Russian segment EVA, so we don't impact that particular EVA. That's the only thing I know of really that's something we're having to watch closely.
Okay, thank you. Let's go to James Dean, Florida Today.
Hi, thanks. So, Mr. Seferdini, I know you think that you'll be able to use this pump module again down the road with some modification. So I just wondered if you could kind of recap where this event, where you think it's left you in terms of how long you expected things to last and average failure rates and all that. As this pump module failing as it has, are you behind where you thought you would be at this point? Do you really think it's no impact if this module can be recovered later, or kind of where does this leave you as you map out the years to come and the spares available?
James, that's a great question, and so I'll try to answer it as succinctly as I can. Every year, we reassess our logistics plan. We look at all the failures that occurred. We look at the statistics associated with those failures and past failures and the design of the unit, and we try to forecast how many spares we need at least up through 2020. And so when we do that analysis for the next year, which starts, I think, at the beginning of the year, so I think we begin that process about early February. When we do the next run, we're going to flow in this failure, and we'll see what it spits out at the other end. What is significant is we think that today we have enough spares in what we plan to build to get us to 2020, at least to 2020. And protecting this pump means if we can find a way to fix this pump or add something to the front of this pump to let us regain its capability, then essentially we still have all the spares we thought we needed before this failure occurred. And you have to remember your analysis assumes failure, so we have to go back and look at this failure and see on average whether it fits in the trade space and see if it affects how many spares we think we need. We haven't done that yet, but we will. And it won't be just this thing we're talking about. We have a certain amount of money we protect to build the spares we need. And so some things didn't fail that we thought were, and so that'll make our position better in those components. Some things failed that we didn't expect, and those make things a little worse. And some things did about what we expected, and so in the end we'll look to kind of balance things out. We do that every year, and we haven't run it in this particular case. It's a fairly complicated analysis process we go through with these ORUs, and it learns from each year that you operate. So it takes us quite a bit of time to run the system run the analysis for all the systems. But that's future work. I wouldn't expect a dramatic change, but it may have some impact on the number of spares we think we need by 2020.
Okay, thanks, James. Any follow-ups here in the room? Okay, we're going to wrap it up. We want to remind you that the Spacewalks are coming up on the 21st, 23rd, and 25th. They begin about the same time every day. Our NASA TV coverage will begin at 5:15 a.m. Central Time, 6:15 a.m. Eastern Time, all 3 of those days. And the actual Spacewalks will officially begin about an hour or so after we come on the air. For all the latest, just log on to nasa.gov/station as we get ready to kick off these Spacewalks. We'll see you back here for our live coverage.